Okay, hello everyone. I'm Sean McManamy. I'm going to be doing this series of videos on Calculus 3. These are just going to be basic ideas covering the topics. And in class, we're going to be getting more in detail and giving you plenty of practice to work on these. So these are just for you to see them and have a basic idea for when we get into class and start working on them. If you're watching this anywhere else, feel free to email me, put a comment in there, and I'll try and get back to you and give you extra information that you want. So our first thing that we're dealing with for Calculus 3 are vectors, dot products, and cross products. So in class, we've already talked about three-dimensional graphing. Now we're going to talk about one of the key aspects of describing mathematics in multiple dimensions, and this is the vectors. So what are vectors? Well, there's something out there already that gives a very good description of this. So I'll let them describe it.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Okay, so hopefully you're not committing crimes with that, but that's a very description of what a vector is. They are an item in math which have directions and magnitudes. In general, they're just going to be arrows. They have a set magnitude or length. They also have their direction that they go in. This can be codified in quite a few different ways. So when we're writing them, we'll use a few different types of notations. Most books and online, you'll see a bolded letter. This represents it as a vector. But since quite often it's a pain in the butt to try and write a bolded letter, you'll often see it with a line over it as well, sometimes with an arrow over the top of it. This allows you to write it down on paper and know it's a vector and not just a simple number. If you have a vector that's going between 2 points, you can write it as this case over here on the right. This allows you to write a vector without knowing too much about the vector except its start point and its end point. And then if you actually know particulars about it, you can write it at the ordered set of values based off of what the components are. Now, the zero vector is somewhat special in the fact that it does not have a direction. It's the only one that doesn't. So while it's still classified as a zero vector, it's missing one of the two properties of vectors. And in general, we have our standard basis vectors for 3 dimensions, where you can see those at the bottom. You have I, J, and K, and those just correspond with the vectors 1 in the x direction, 1 in the y direction, and then 1 in the z direction. So those are the basis ones that get used fairly often. Now, some of the basic things we can do with vectors is we can add them. So there's a couple of different methods that we can deal with. Some of them are visual, some of them are actual computational. So you have your parallelogram method. You have a triangle law, and then you can just actual add them. So the actual adding, yippee, it's adding component-wise. So x values get added with x values, y values get added with y values, and so on. And you do a similar thing for subtraction. For this one, you use it to subtract the values instead of adding them. Now, we'll come to the diagrams for the 2 other methods of adding. But if you have 2 points, x and y, and you want to have a vector that's going between them, then the vector going from x to y, well, you subtract them in the opposite direction, so y minus the x values. You have to keep that in mind because the ending point is where you want to be, so that's positive, and you want to take away where you were. Now, here's what the parallelogram method looks like. You essentially copy over your 2 vectors to the ends of each other and have them at the same starting point. And then going from original starting point to the end of the second vector for each, that is your new addition vector. Now, the triangle law is essentially the same type of thing. It's just you don't complete the other side of the parallelogram. And instead of just copying over one of your vectors to the end of the other one, you just put your vector at the end of the other one. This method works a lot if you're dealing with actual items and you can move them around yourself. If you can't move them around, then it's not quite as useful. And as you can see over here, if you're doing subtraction, then it's just going from one point of the vector to the other vector. And they're still at the same base point. The other thing we can do with vectors easily is scalar multiplication. So if you have a scalar, c, and for those of you who don't know, a scalar is just a singular value. It might not be real, it could be in the complex plane, but it's just a singular value. And then you also have to have a vector. If you multiply c by your vector, then you'll just scale it by the magnitude of c. So if c is 2, it's just going to double everything inside your vector. Now if c is negative, it's going to make us go in the opposite direction. If a is if c is positive, a will keep going in the original direction. And as I said, all you do is take c and multiply by each component wise. So that's all it's doing for scalar multiplication. Now, if your scalar multiplication comes out to 0, either your scalar is 0 or your vector is 0. That's always going to be the case. When we're dealing with products later on, that's not necessarily going to be true. So here's a couple of examples of scalar multiplication. So we have our original scalar v. We have 2v, so it's 2 times our vector v, and it's twice as long, going in the same direction. 1/2 v, well, going in the same direction, but it's only half as big as original v. And negative v, which is -1 times v, is same size as the original one, but just going in the opposite direction. So that's some of the basics of vectors. We'll cover a few more properties in class. But now let's talk about the dot product. So what is the dot product? If you have your two vectors, then the dot product of them is given by the piecewise multiplication of the products, or the components, added together. So your x terms are multiplied together, and then your y terms are multiplied together, your z terms are added together, and then you add them all up together. Now, this works in multiple dimensions beyond just 3. So 2 dimensions it works. 1 dimension, it's just the standard multiplication. And then 4 dimensions, 5 dimensions, it does not matter how many dimensions, it works, as long as they are both the same dimension. So you can't have A be in 3 dimensions and B in 4 dimensions and do a dot product. It will not work. Now, here's one of those funky things. A and B are orthogonal if and only if A dot B is 0. So for those of you who don't know, orthogonal means the angle between the two vectors is a right angle. So if the A and B form a right angle with each other, you automatically know that the dot product is going to be 0. And if vice versa, if you know the dot product is 0, you know that they're going to have orthogonal angle between them. Another type of product is the cross product. This one's slightly different, and this one is slightly more computational as well. So for the definition, if you have your two vectors and you want to do a cross product of them, you're going to have to find a determinant of the 3x3 matrix given here. Order is important. So if A comes first, A is going to be the middle row. If B comes first, B is going to be the middle row. If you do it the opposite direction, it'll end up giving you a different vector at the end. Now, some of you might not know how to do determinant. We're going to do a lot of that in class, but we have the basics here that I'll explain in a moment. Now, here's another situation. A cross B is orthogonal to both A and B. So A cross B is going to give you another vector, whereas the dot product was only going to give you a scalar value. And this new vector you're getting from here is orthogonal to both of the previous vectors you had. Now, if this one comes out to 0, it means that A and B are parallel with each other. So in the previous situation, for the dot product, it only comes out to 0 if they're perpendicular. Here, they only come out to 0 if they are parallel. Slight differences there. And then there is something called the triple product, where if you have 3 vectors, you essentially just do the dot product with a cross product. And what's nice about that is you can actually replace the I, j, k with the values of whatever value vector is getting dot product in. So here's a quick example of what a cross product ends up doing. It has the 2 vectors A and B, and the cross product is perpendicular to both of them. Now, let's quickly go over how to calculate a determinant. So you have this 3x3 system. What you do is you take the value in the upper left spot and put it out there by itself. Cross out that row in the column that corresponds with that value, and then you want to take a smaller determinant of that. And then you want to do it for the next value in the top row, and then the next value in the top row. And that's it. Alright? Now, there's a slight issue here. I accidentally put a plus instead of a minus on the J. I'll make sure to edit that. So, and finally, you're going to want to have the determinant of the smaller values, which those you just do the diagonals. The proper diagonal is positive, the backwards diagonal is negative, and you just multiply those values together, and that is your determinant. So hopefully this helped, and I'm going to see you in class.